Good morning, good afternoon, good evening, good wherever you are today. And welcome to another SNIA-NSF, or the Networking Storage Forum, presentation. This one on NVMe-oF fabrics, looking beyond performance hero numbers. So hopefully you're at the right presentation today. So without further ado, I'd like to welcome our speakers. My name is Alex McDonald. I'm an independent consultant. I'm the vice chair of the SNIA-NSF. And I'm joined today by three very, very high grade, when we're talking top-notch, top quality people here. Erik is a distinguished member of the technical staff working for Dell's CTIO group over the course of his 24-year career. So he's been around a bit. He's found a passion for connectivity automation, loves helping end users understand technology, as well as how to deploy it. And his specific area of expertise is in storage networks, with a focus on block storage protocols. We're also joined today by Nishant, who is the Director of Emerging Technologies at Marvell, and focused on the intersection of networking and storage. In other words, the bit between where we keep it and where we move it around. Prior to joining Marvell a decade ago, Nishant made significant contributions at various storage and networking industry major companies, including Hewlett-Packard, Sun Microsystems, remember them, and Intel. And Nishant continues to be inspired by the work of Erik that Erik and Rob have done, which is a really nice introduction to Rob, who's the Vice President of Storage Technology at NVIDIA Networking Business Unit. He focuses on ways to apply high-speed interface technology to storage systems. As a technology leader and visionary for more than 35 years, he's been a key evaluator and decision maker for the development of storage networking products, not only at NVIDIA, but also Minox, QLogic, and Anchor Communications. So today we have a fabulous group, three people who really, really do know their stuff. Welcome, guys. SNIA, just a brief overview of SNIA before we start. SNIA is 185 industry-leading organizations. We've got about 2,000 active contributing members and about 50,000 IT end users and storage pros worldwide, of which you in the audience are some. You can learn more about SNIA at SNIA.org, and in particular /technical, where we describe the technical work that SNIA covers. Storage and networking are our favorite two topics. You can also follow us on Twitter at SNIA. What does the Networking Storage Forum cover? Well, these are the technologies that we cover. It's pretty wide-ranging in terms of the hardware, so Ethernet, Fibre channel, InfiniBand, and then the layers on top of it, things like iSCSI, NVMe-oF fabrics, NFS and SMB, the file protocols. We cover virtualized, hyperconverged, software-defined storage, and storage protocols like block, file, and object. And we're also interested, who isn't these days, in making sure that data is secure, and we've covered these topics in the past as well. So just a quick legal notice about this presentation. There are no warranties with it. So if anything you do with this presentation causes whatever you do it to break into 2 bits, both of them are yours. But this project is this presentation is a project of SNIA, and we would like you to honor our copyright and at least attribute us if you use any of this material. None of us are attorneys, by the way, so take legal advice. So without further ado, I'm going to introduce and hand over to Nishant, who will take us through the start of the presentation. Thanks, Nishant.
Well, thank you, Alex. And this is Nishant, and I have kind of the pleasure here to kicking off this conversation and into talks that Erik and Rob would do right after my chit chat here. When we put together this topic here on beyond hero numbers, which was the idea that Erik had, we figured it's best to start off by setting the state clean and defining what we as a team mean by hero numbers. And we all have heroes in our life, and heroes have values in our life, but there are heroes and then there are real people, so to speak, in my words. To us, hero numbers are, they are performance metrics which which indicate what is theoretically possible. They are often measured at the extreme ends of the capabilities of this particular transport or a device under test. And typically hero numbers are the very maximums something can achieve, and talk about latency and generally IOPS or bandwidth. They do not sometimes talk about the cost of IOs, for example, the CPU cost of IOs and things like that. And more importantly, hero numbers are typically classified under ideal conditions. And the big challenge with all of these things in what hero numbers are is that in real life that mileage may vary significantly, because hero numbers is not something that you would typically see in a real world environment. And if you are going to deploy a system based on hero numbers and hero numbers alone, you will be in for a surprise, because end of the day, it's not just the performance of a device, and in this case, performance of a fabric, that will determine how successful your deployment is going to be. But it's the all-encompassing thing, right? It's the skill set of what you have if you want to deploy a technology or a device. The cost of it, the security considerations, the operational considerations of all of that. So what we wanted to do here in this presentation is two very important things, right? A, help you distinguish between hero numbers and real numbers and compare and contrast, and Erik will do a lovely job in that, I'm very confident, in which he will show you the areas where typical hero numbers are being talked about and touted, and he'll talk to you about the real world and contrast how different the real world performance metrics are versus the hero numbers. In addition, as a team, we want to provide you context on everything that should go about in your decision making about what kind of storage fabric you would want to choose, right? And so we'll talk about, in some ways, cost or cost of operations, security, bunch of different use cases and applications that will eventually, all of that will help you understand how to enable you to make a decision, and the right decision for your environment or your customer's environment, whatever that is. With that, let me, at a very high level, and we'll use this slide to help you walk through the rest of the talk here. When we look at customers and we look at NVMe or fabrics that our customers are going to deploy, and these customers could be across a range of medium-sized customers to large enterprises to telco workloads to high-scale cloud workloads. But what do these customers expect from fabrics is something very common, right, across these segments. And it's a no-brainer, is definitely cost, which is a big portion of the conversation. And the cost could come in two ways. There could be cost of just operations. If a specific technology or fabric is extremely hard to manage for that specific customer, the cost of operations could be high. The other thing could be a cost of a rip and replace, right? For example, a lot of the customers initially have investments in fiber channel. And with fiber channel, the HPAs and the switches that customers already had already support FC and VME. And I'm a little bit jumping ahead here, but some of those costs do not need to be incurred on day one, right? Similarly is operational simplicity. Even if you got the cost right, day-to-day operations are extremely important, both in terms of the cost of operations as well as the cost of making mistakes during operating a specific fabric. There's definitely performance, which is what Erik is going to talk about here shortly, and performance beyond hero numbers, and we'll spend a lot of time clearly classifying the hero numbers versus the real numbers. And there will be some of you who will be in the hero area, and absolutely, but there will be a big chunk of you guys and your customers who are in the real area, and we'll talk about both. And then there is always the conversation of applications, right? Depending upon what kind of applications you have, where those applications live, and what is your network environment, and what is the scale of that environment will all determine what fabric is right for you. And both applications and scale, you'll hear a lovely perspective from Rob Davis on three different kind of big chunks of big categories of applications. And then I'll come back and talk about security. And although security is put in last here, I'll come back and say that, hey, security is extremely important and it should not be an afterthought. And there is being work done around the standards bodies to bring security for NVMe or fabrics into play. But all of these things, in many ways, a very equal participation that will play into the overall decision making. And we'll walk you through all of these in the presentation today. Excellent. So let's talk about a little bit about the future of storage fabrics. And I wanted to kind of give you a little bit of a journey kind of overview with this slide. On the left-hand side is my view of where we are today, right? And we are in a heterogeneous world of storage fabrics, right? All of us who have lived and breathed in storage and networking are kind of well aware that customers choose different technologies and different storage fabrics based on a plethora of different things, right? Their own environment, their skill set, past history, so be it, right? What we have today is primarily, fiber channel connectivity. It's popularly used for accessing external storage, air-gapped network, popularly used for business critical applications. Then there is iSCSI. If you talk about Ethernet-based infrastructure, there is iSCSI and FCOE, which is today mostly used in blades and converged kind of environments. And then there is hyperconverged infrastructure, HCI, which is compute and storage put together in nodes and then clustered together. And there are solutions like vSAN and Azure Stack and many others, equally good solutions that exist today. My view and our view of this panel is that a lot of what you see here in the left is going to slowly transition into what we see here on the right. And we will be transferring from one heterogeneous world of fabrics where customers chose a storage fabric for a variety of reasons. And those reasons, like I said, are not changing, right? The same reasons will then allow the customers to make a determination on what is the NVMe or fabric, or what is the future fabric that would work for them the best. At least my view has been that a lot of fiber channel customers would likely continue and leverage their investments in fiber channel connectivity by moving to FC NVMe or NVMe or fiber channel. Most fiber channel products that I have seen provide concurrent operation between traditional fiber channel and FC NVMe, providing a seamless path, because we know customers don't turn off one switch and turn on another. There is years, if not several years worth of migration that happens. For Ethernet-based fabrics like iSCSI and FCOE, we expect a transition into NVMe over fabrics on Ethernet. It could be NVMe over RoCE, it could be NVMe over InfiniBand, or NVMe over TCP. And we'll contrast all the different fabrics within the Ethernet space with you guys shortly here. In addition, for hyperconverged systems, which today most hyperconverged system, and again I say most because there are always exceptions, rely on standard TCP networking. We expect that to continue forward, but we also see that RDMA, both RoCE and its TCP variant IVORP, to have a future potential use case in hyperconverged systems. And a lot of this transition from left to right is driven by the fact that NVMe and all its low latency capabilities require a very efficient fabric to marry with it. With a little bit color on one heterogeneous world to another, I want to take a slightly deeper view on all the different use cases, as well as a bunch of different applications that could potentially map across the different fabrics. And I'll spend time talking about three fabrics here, just for purposes of simplicity. I'll bucket one as NVMe over RoCE and NVMe over InfiniBand as one section, and then second would be NVMe over TCP, and then finally an FC NVMe or NVMe over fiber channel. Right, and my purpose of putting this together is to provide a view of how we see all the different applications map across different fabrics. And the indication here is just, it's not about that these views are are hard-coded, so to speak, but they're indicative, they are preferences, they are things based on experiences and visibility that we have had. Let's start here from the kind of right-hand side here. Most in-house BCAs or business critical applications, high-density virtualization, business-critical databases traditionally run on Fibre channel, and the expectation is many of them would transition to NVMe or FC NVMe to make that a natural choice. In the middle here is NVMe over TCP, which is kind of general purpose fabric, allows you to kind of scale at ease using any available networking device and not really special infrastructure, and could be used for literally any applications under the sun. And it's well placed in between here. And on the very left-hand side is NVMe over RoCE or NVMe over InfiniBand, both. And you'll see some contrast between these two fabrics that Rob will bring out when he comes on stage here. But NVMe or RoCE is extremely low latency fabric and very popularly used in machine learning, a lot of HPC applications, and a lot of databases like Cassandra and Mongo, which are very DAS-centric and enable the scalability of DAS using NVMe over RoCE. And if with all of this context that I put together, if we overlay some of these use cases, if you look at extreme high performance use cases, extreme low latency use cases, NVMe over RoCE or even NVMe over InfiniBand absolutely is the most efficient of those fabrics. But if you look at kind of high general purpose use cases, TCP and Fibre channel show up on the top of that, and then definitely there is always NVMe over RoCE. In addition, most business critical applications, traditional enterprise class business critical applications probably run very well on Fibre channel as well as on NVMe over TCP, and a lot of specialized use cases.
Thanks, Nishant. And hello, everyone. This is Erik Smith again, and I'm going to start by talking about protocol performance. But before I jump into the performance testing results, I wanted to quickly review how we captured the data. To start with, the graphs in the following slides are based on testing performed at Dell Technologies. We started to perform this kind of testing a few years ago for the purpose of comparing the fabric types that are available for use. In other words, all things being equal on both ends, we wanted to determine the theoretical benefit of using one fabric type versus another. Now, we began this type of testing because of the very optimistic performance benefit claims that were being made when NVMe over Fabrics was first being introduced. More specifically, some were claiming NVMe over Fabrics would provide an order of magnitude or 10x performance improvement when moving from single queue SCSI and onto multi-queue NVMe. Now, to make a long story short, our testing revealed that while the combination of NVMe and multi-queue provided a significant benefit, it was not 10x. I also wanted to point out that these test results do not represent what you will experience when using one fabric type versus another on every storage platform. This will be much more dependent on the storage platform implementation than on the fabric in use. Also, the test configuration itself consisted of an EasyFIO client running on a physical Dell server, running Linux that has an appropriate adapter type installed. So for example, 32 gig fiber channel, 25 gigabit Ethernet, or 100 gigabit Ethernet, as well as a single 32 gig fiber channel or 100 gigabit switch that was used for SAN connectivity, and an LAO target running on a physical Dell server, running Linux that's using RAM disk for storage capacity. Now, the test results shown are all 4K random writes performed with varying numbers of threads. Now, we'll start our comparison with IOPS and point out that 100 gigabit Ethernet, whether it's RoCE or software-based TCP, provide higher maximum IOPS than the 25 gigabit Ethernet and 32 gig FC NVMe solutions. And this isn't surprising because 100 gigabit Ethernet provides roughly 4 times the bandwidth as 25 gig or 32 gig fiber channel. And bandwidth divided by average block size, 4K in this case, gives you the maximum IOPS possible on a given fabric type. So from a theoretical point of view, it makes sense that using a higher speed adapter could result in higher IOPS in general. And our test results support this. You'll note the difference between the fabrics. Each fabric increases as the number of threads are increased and reaches a maximum at the far right-hand side of the graph, which is associated with 256 threads. Now, when my colleagues and I look at this chart, we tend to focus on the middle region, where the performance delta is much more modest. And we do this because this is much closer to the types of operating parameters that many customers and applications will be working with. The area all the way to the right-hand side of the graph is interesting to note, but I would consider them hero numbers and would recommend not placing too much importance on them unless you are pushing the upper limits of what is possible with the fabric type you are using. Now, I also want to point out that I've chosen these fabric types because they seem to fit best into the general purpose category that Nishant was referring to earlier. Later in the presentation, Rob will add some detail about InfiniBand. Now, while IOPS are important, another metric that is of even more interest, especially as we shift to real-time prediction and decision-making applications, is latency. Now, with regards to latency, on this slide, lower is better. And we can see the absolute lowest latency is shown all the way to the left of the diagram. Now, as with the previous chart, we prefer to focus on the middle of the graph. And again, we do this because it's more realistic given what we know about our customers' workloads. The area all the way to the left would fall into hero number territory because the data represents the lowest latency recorded and will not typically be observed by our customers under normal operating conditions. Now, with regards to the middle of the graph, you might be wondering, why would they just go ahead and use the fabric that provides the lowest latency? It will provide some benefit after all, right? And the answer is yes, there will be some amount of benefit, but the benefit might not be significant enough in order for it to result in a meaningful difference to your application. And the reason is related to a couple of important points to note about these latency measurements. First of all, they represent the fabric latency only and do not consider the latency associated with the physical media, nor the latency added when storage services such as dedupe, encryption, protection, and so on are included. And two, these latency measurements were captured in an uncongested fabric. And as a result, things like the impact of congestion and how it interacts with error recovery are not being factored in. The danger here is one of the fabrics involved might recover from congestion in a more timely manner, or might be able to avoid congestion altogether. Now, during our testing, we noticed that congestion had a significant impact on some fabric types and not others. We also noticed that there were significant differences between the different adapter vendors and their ability to recover from congestion in each fabric type. Now, all of this should just be interpreted as your mileage may vary due to a wide range of issues that are specific to your application and operating environment. I would just encourage you to keep this in mind as you perform your own testing in advance of deploying one fabric type versus another. So far, we've looked at IOPS and latency as they relate to the given fabric types. And while these metrics give you some valuable data points, we think looking at other metrics can yield some other interesting insights as well. For example, we also like to look at the number of IOs per percent of CPU utilization. In this case, higher is better. This is an interesting way to look at the data, but because it implies a fully offloaded TCP solution could perform more useful work on behalf of applications rather than on moving data. Now, please note the data behind this chart was from a different set of tests, and as a result, the names of the plot lines are different. However, the data is consistent with the other tests. In the area of interest, the fabric types are close enough to say that, at least from a performance perspective, they are more or less equivalent to one another, especially when used for general purpose connectivity. Next, I'm going to cover some considerations about cost and operational simplicity. So right off the bat, based on the data presented so far, these three NVMe Fabric types have more or less equivalent performance attributes, of course, assuming that you're all running the same link speed, 25 gig versus 100, for example. Now, from a software-defined storage perspective, based on the solutions that are available today, it seems safe to say that Fibre channel is generally not used for software-defined storage. So I'd suggest keeping this in mind if you are thinking of going down this path. Now, the centralized provisioning category is the ability to control connectivity from a single location. In the case of Fibre channel, connectivity is controlled via zoning, which is configured by interacting with the fabric. Today, with NVMe over an IP-based fabric, connectivity is configured from the end devices. And this is generally viewed as a limitation. It's kind of like configuring iSCSI. Now, the blog post reference below will provide more information if you're interested. And while the good news is this limitation is being addressed by an entire group of companies, and we'll have centralized discovery for NVMe over an IP-based fabric really soon. Now, this, for me personally, this is a huge area of interest. And it's being tracked under NVMe.org's technical proposals TP 8009 and TP 8010. Now, for more information about these technical proposals, you can check out the SDC 2020 presentation titled NVMe Fabrics in the Enterprise. State change notifications allow for end devices to understand when something in the fabric changes and are an essential part of automating storage connectivity. And with regards to the edge and distributed systems at scale, or cloud operating model and automation categories, we believe TCP is the best fabric to use. Edge is generally not going to make use of Fibre channel, and RoCE, due to the recommended and in some cases required use of DCB, can be a bit of a bear to work with in an automation context. That said, there are several proprietary solutions available to help automate the configuration of a fabric if you wanted to use RoCE. And finally, the CapEx cost advantage goes to Ethernet, and it isn't even close. Fibre channel is much more expensive on a dollars per port or dollars per gigabit perspective. And as of right now, I think the best case hardware list price found via Google search has 32 gig Fibre channel coming in at multiple times the cost of even a 100 gigabit Ethernet based solution. So 100 gig can provide up to 4 times the performance, and you can get it for a fraction of the price. But Fibre channel provides a centralized set of fabric services that have been around for 20 years, as well as 20 years of maturity, meaning it's extremely stable. Now, if you decide to go Ethernet and you're trying to decide between TCP and RoCE, keep in mind, as Nishant mentioned earlier, and as Rob will explain in a bit more detail later, the answer might be both. But some of the things to keep in mind there are performance. I think it's pretty much a wash. Both RoCE and TCP perform really well. And so are there use cases where RoCE will be better? Absolutely yes. And the same is true for TCP, especially offloaded TCP, and especially for general purpose connectivity. Now, in regards to interoperability, we've seen some variability between RoCE implementations that can lead to interop concerns. The biggest one of them might be how packet loss is handled. Well, some implementations have become exceptionally tolerant of loss and can recover from it without the user noticing anything. Other implementations still have a way to go. And for these implementations, as well as the environments that contain multiple RoCE adapter implementations, the best practice is still to configure DCB lossless or lossless Ethernet from end to end. Now, TCP just works, and this is why I like it so much, and I think you will too. Interoperability testing costs are going to be high for RoCE for the reasons I mentioned above. In terms of network congestion impacts, RoCE is usually run over a lossless network, and like all lossless networks, can be susceptible to congestion spreading. TCP, although it had been proven to benefit from lossless Ethernet in some configurations, expects packet loss, and in fact depends on it to determine how much outstanding data it can have with a given destination. Network management impacts. Now, for me, it's all about troubleshooting. And if you've ever, and the reason is because if you've ever attempted to troubleshoot a slow drain device with Fibre channel, you understand how hard it can be to locate the problematic end device. This is in spite of years of work by the Fibre channel industry to create the appropriate tools that help end users deal with these kinds of issues. Ethernet does not have anywhere near the same level of functionality when it comes to troubleshooting congestion spreading, and this would be a concern for me if I were to consider RoCE. Since TCP just works, more or less, it's less of a concern. Another very important consideration to take into account when choosing fabric type is manageability. Or put another way, the ability for a given protocol to fit into your current provisioning workflow. I think a reasonable way to start thinking about the differences between the fabric types is to consider the number of initial configuration steps required. Now, before I jump into those details, I want to point out that these fabric types can be broken down into 2 broad categories: those that support a network-centric provisioning model, such as Fibre channel and FC-NVMe, and those that support an end node-centric provisioning model, such as NVMe TCP or RoCE currently do. For the Fibre channel-based fabrics, provisioning involves installing an HBA, zoning the HBA to a storage port, and then LUN or namespace masking on the array itself. Following these provisioning steps, the host can use the Fibre channel fabric's name server to retrieve a list of storage interfaces, log into them, and then retrieve the list of LUNs or namespaces that have been allocated to them. When changes need to be made, such as adding a new storage interface, the fabric will notify the host after the change has been made using a registered state change notification, and the host will discover these changes automatically. For NVMe TCP and RoCE, the hosts need to be configured individually to access the correct storage resources, and this can be quite a bit of work. Now, provisioning TCP involves configuring the network, basically configure VLANs and the switch interfaces to allow those VLANs. And then on the host, you need to install the appropriate driver and configure the IP interfaces. Then you need to configure the storage subsystem, which may include configuring IP interfaces, as well as namespace masking. Provisioning RoCE involves many of the same steps as TCP, with the notable addition of needing to configure end-to-end losslessness across your IP SAN. Now, while there are proprietary solutions available to help automate some of these end-to-end configuration steps, these solutions typically only work when running in a homogeneous environment. Now, I do feel compelled to point out that as challenging as we found the process of configuring end-to-end losslessness, what really caused us trouble was validating that we had configured it correctly. And as I mentioned before, troubleshooting was also a challenge. Both of these can be addressed by adding additional functionality, and I think it's just a matter of time before that happens. And with that, I'll turn it over to Rob for his comments about the applications for NVMe over Fabrics, as well as some considerations about scale.
Thanks, Erik. Hello, everybody. As Erik said, I'm going to be telling you about the applications that are using NVMe over Fabrics today, and also show you where they fit into the data center at scale. So basically, where's all this performance Erik showed us going in the data center? And what's interesting is, although Erik beat up RoCE quite a bit, this was the first NVMe over Fabric application to go to market. On higher-end all-flash array systems, the refrigerator-sized ones, they have a capacity expansion kind of JBOF connected over JBOFs connected over a hidden network or fabric, usually inside the enclosure. And NVMe over Fabric replaced much of the PCIe and SAS fabrics used in earlier designs with either InfiniBand or Ethernet fabrics using NVMe over Fabrics on RDMA. And NVMe over Fabrics mostly at 100 gig because it provided much higher bandwidth, which we didn't really talk a lot about earlier, but obviously the bandwidth between a 32 gig fiber channel and a 100 gig Ethernet or InfiniBand is going to be dramatic. And also provided the needed support because these NVMe SSDs were much more performant than the earlier hard drives that Fibre Channel was designed for. And RDMA provided both that bandwidth and consistent latency, which is super important to this kind of application. When looking at the left side, you might wonder what the performance difference is between RoCE, RDMA over Ethernet, and InfiniBand, to which basically InfiniBand RDMA is the native protocol, so it's not really over anything. And that in a nutshell is the difference, because IP is the native protocol for Ethernet, obviously. And so RDMA sits on top of that IP layer. And from a bandwidth perspective, as you can see, they're pretty much the same. But from a latency perspective, there is a difference because of that native RDMA versus the layering of the RDMA on type of Ethernet. Also, there's a difference because the hardware for InfiniBand, you know, the history of InfiniBand is the world of HPC back, 2000, I think, when it became sort of prevalent there. And so all in HPC, you've got a cluster of servers that are put together to make a supercomputer. So it's been designed for performance from the beginning, very low latency. And so the difference you see isn't really much. If you're just talking about an adapter, it's about a half a microsecond difference with the best RNICs to multiple microseconds, sort of depending on vendor. But you also have to remember that there's a switch involved. And with the switch, you add, you know, probably about a microsecond difference with the best switches. And again, it depends on the maker of the switches. And it doesn't seem like much, a few microseconds, but it adds up when you consider that the fastest SSDs have less than 10 microseconds latency. And you need to pass through the switch and adapters at least twice for each rewrite transaction. And also, there are often 3 or more switches in the data path. So if you're not paying attention, your NICs and switches, to your NIC and switches, you can easily double your data path latency. The next application where NVMe Fabrics has taken hold is what we call classic SAN environments, the traditional home of Fibre Channel and iSCSI that Erik talked about at length. And what NVMe Fabrics gives you here is the performance improvement. Erik showed the latency protocols in his slides for classic SAN, and while keeping what it also gives you is you keep those well-known SAN features, you know, the better utilization, scalability, management, fault isolation, all the things that SANs were invented to fix. Now you do see InfiniBand sometimes in this architecture, especially in those HPC supercomputer data centers. Also in AI clusters, you know, clusters of GPU in traditional data centers, which are becoming more and more popular because of the advancements of artificial intelligence across business applications. And now you also see InfiniBand in cloud HPC, where the hyperscalers, you know, the providers of platform as a service are allowing users to rent supercomputers in the cloud. And just like with the last slide, you might wonder what the performance difference is between traditional iSCSI in a SAN, and because we have Ethernet for NVMe Fabrics, we can compare those two. And this is, I kept the speeds at 25 gigs, so you can compare that with Erik's slides on Fibre Channel and NVMe over TCP, because this was done with RoCE, and get a good idea of how those transports would look if you just take his slides and compare them. But remember to keep in mind that with Ethernet and InfiniBand speeds of 100 and 200 actually has been out for a while, and next year 400, the bandwidth comparisons to Fibre Channel are really not relevant. But you can get a good idea of the 25 to 32 comparison. These charts show how iSCSI and NVMe Fabrics on RoCE compare when providing SAN connectivity to a network of servers running a common enterprise virtual operating system across increasing message sizes. The test was run under heavy load so that we could simulate the storage workload these servers would have with many, many VMs, and would put the load it would put on the SAN. And what it shows is that with NVMe Fabrics, you can have a lot more VMs per server and still maintain the high performance level. This NVMe Fabrics application has many names, but compute storage disaggregation is what I'm calling it here, has really been enabled by NVMe Fabrics. And that's because of the extremely close, and in some cases even better than local NVMe SSD performance you can get with NVMe Fabrics on Ethernet, and of course Ethernet's economical cost. And basically here's how it works. So what you do is you remove the hard drive, or the the SSDs from the compute, and put them in JBOFs, high performance JBOFs at at least 100 gig Ethernet with NVMe Fabrics. And by removing those drives, you get to increase the efficiency of your compute racks, because instead of getting, you know, it's roughly 30% efficient use of a local drive, you now jump to 70%, which is the usual percentage for remote storage. And because it's in the rack and only through one switch, you can use RDMA without any issues for tuning the network, and get performance that in many cases is better in some cases, but always at least within a couple microseconds of the local drive performance. And this enables the data center, especially very large data centers where this is a big factor, to improve their efficiency of the storage they're buying by 50%, which is huge. In this application, there's two other ones here actually. The first one is called scale-out storage, or software-defined storage. And this is when you take a software and a cluster of commodity servers, and you provide the same kind of functions that those refrigerator-sized systems we talked about back in the beginning provide. And what NVMe Fabrics allows you to do is increase the performance dramatically because of that ability to be close to local. And when you take that software, that same clustering storage software, and put it in a VM, you get hyperconverged. And again, the capabilities of the NVMe over RoCE, and in some cases, depending on the performance, the NVMe over TCP gives you the ability to now run much higher end applications on those clusters, on those HCI nodes, because of the performance improvement that allows you to scale them across multiple nodes. And the last thing I'm going to talk about, application, is NVMe, using NVMe over Fabrics for artificial intelligence. Many artificial intelligence applications require extremely large, like hundreds of terabytes or more data sets. And just to move this data takes the highest bandwidth you can get in your network. But because GPUs can consume it so much faster than CPUs, you need to move it as efficiently as possible. And this is being done with GPU direct storage. Before GPU direct storage, the data is first moved from the SSD to the memory of the SSD driver, and then to the network driver, and then it moves from that memory stack to the other, and then the network adapter sends it across the network, where it moves into the network stack of the GPU host of the CPU that's hosting the GPUs, which moves it to the host memory, which then the AI application finally gets access to it and can move it into GPU memory. With GPU direct storage, all of that's many of those steps are bypassed. Using RDMA, you're able to move the data directly from the system memory of the storage system across the network and into the GPU memory, which causes a dramatic increase in performance, as you can imagine. And there's some new technologies coming, CMB, or control memory buffer, which is controller memory buffer, which is an NVMe.org standard. A new technology in SSDs actually removes that actual transfer into system memory on the storage system side, because now that RDMA adapter can move the data directly from the SSD across the network, bypassing now one more system move through the CPU. And then another technology called EBOF, or Ethernet, which uses Ethernet SSDs. Now, as long as they support RDMA, again, you can move that data directly across the network into the GPU memory, giving you that much, much higher performance needed for artificial intelligence applications. And lastly, I'm going to show you where those fit into the data center wide architecture. And this gets a little complicated. So let's take it one transport at a time, and we'll start with the easiest, which is NVMe over TCP, because it works everywhere, because it's IP, TCP IP. At my company, for example, we've run it from our lab in Israel to our lab in Sunnyvale across the internet. As you can imagine, the performance was a little less than what Erik showed, actually way, way less. But it worked. And so for moving data from data center to data center with NVMe over Fabrics, that's the way to go. Of course, you've got to take into account the performance and cost advantages that we talked about earlier. NVMe over TCP, but is the hands-down choice for data center to data center. In GPU clusters that I just talked about on the far left, you probably have InfiniBand or RoCE because you need RDMA for GDS. Inside high-end storage systems that I talked about in the first slide, of course, it's going to be InfiniBand or RoCE as well. Again, that's sort of depending on performance, because there's no reason you couldn't use NVMe over TCP. Across data center at scale, you find Fibre channel, TCP, NVMe over TCP, and RoCE. As Erik said, it takes a little bit more expertise in your network to implement RoCE, but in fact, most of the hyperscale data centers today use it, so obviously it can be done. And with that, I am going to turn it back over to Nishant to cover how to keep all this super high performance data secure while we move it around the data center.
Thank you, Rob. It's always a pleasure and very entertaining to listen to you. I appreciate it. Great insights, and kind of like you said, right? The NVMe TCP is likely the easiest choice, and it's definitely the fiber channel customers who have existing investments and likely carry forward. And while there is a little bit of pain to deploying RoCE, but there is something to gain too from that, right? The absolute lowest performance. So it's an interesting mix of things, and I don't like to say it or hear it that end of the day your mileage depends, but that is the truth here. And the sole purpose of us talking to you guys is giving you the perspective of ours from our experience about cost, simplicity, performance, all the different applications, the scale, and depending upon where your application is, and whether you want to run between Israel and Sunnyvale or within your racks, your choice of fabrics depends on that. Last, and in many cases an afterthought, is security. And I have a twofold purpose here. First, I want to scare you a little bit that there are security threats with NVMe or fabrics. And once I've successfully scared you, I'm going to propose a solution to it. And that's a simple sales tactic, not that I'm in sales. Back to security, whether we realize it or not, when we use NVMe or fabrics or variants of NVMe or fabrics that we have all talked about, in many cases, data is traversing the fabric in clear text, right? So taps and sniffing devices under the floor outside your data center could easily read your precious data. There could be rogue storage devices. They could enter into your network, expose namespaces that mimic other namespaces, and steal your data, or worse, silently corrupt your data, which you won't realize until the time when you need to read it back again and use it. There could be also recon things that hijackers could potentially do by listening in on your sessions and picking up the key metadata as well as potential data, which they could use to then mount a large-scale attack. Net of this is that with NVMe or Fabric, just like with many other traditional storage fabrics, I/O is going out in clear text, and these threats are real and present and clear in many scenarios. And it is absolutely essential that customers like you guys, or customers that you advise, invest in securing NVMe or Fabric's data, both while it is in flight as well as when it is at rest. And at rest, a lot of people do it. It's a great idea. But even in flight, it is essential. There is a couple of things, all very standards based around NVMe or Fabrics and securing NVMe or Fabrics. For Fibre channel, there has been for many years a standard called FCSP2, which applies to FCNVMe, and that enables a clear-cut mechanism to help authenticate different Fibre channel endpoints and entities, to set up keys, ensure frame integrity, confidentiality, and distribute security policies across the Fibre channel SAN. And the beauty of this FCSP2 is that it can work on FCP as well as FCNVMe, so both traditional Fibre channel as well as NVMe or Fibre channel concurrently. And there are many HBAs in the market that provide full offload for FCSP2. And it's industry standard, complete interoperable. So, it's something I would strongly encourage you guys to consider, that while many of us, encrypt our data at rest, it is at risk when it is in flight. There are industry standards. There are full offload solutions out there. So your cost of implementing a encryption of data in flight is not going to be too high. It's something you could, well, a cost of a breach could be significant in terms of lost credibility, lost data, and things like that. For Ethernet-based fabrics, there's definitely transport layer security with NVMe or TCP, as well as IPsec that you could use at a lower level for TCP as well as for RoCE v2. Both of these are standards and provide privacy and data integrity across the fabrics. And just like the Fibre channel scenario, there are many NICs out there in the market that provide full offload for these. So again, your cost of implementing security is not going to be too high. A special note on TLS here, the NVM Express group is working in a TPAR 8011 to support TLS 1.3. So something to look out for. With that, there is a webinar that we are doing in a couple of weeks from now that I think will show up towards the end of the slide, and Alex is going to talk about. It's going to take deep dive into all these topics of security. I know I'm going to be there in that webinar and a couple other interesting speakers. So I look forward to that, seeing you guys there. With that, I was going to kind of show this slide, all the things we talked about, pass it over back to Alex for any of your questions that we can take.
Thanks, Nishant. That's very helpful. Yeah, just let me move forward one slide, actually. I think the slide is, before you do that's the slide that you wanted to talk about. We're going to be doing a webinar on the security of data on NVMe-oF fabrics, the armored truckway. So that will be an interesting topic. I'm not quite sure what armored truck security for NVMe looks like, but hopefully we'll find out. If you want to register, by the way, just do so at that link there. You'll see that at the bottom of the slides. We've had several questions. I'm not going to do them all. We don't have enough time to do them all, but there's one I wanted to get to because it seems to be a real poke you in the eye question. And I think this is for all three of you. I'm going to take it one at a time. I'm going to get Rob to answer it first. Let me phrase the question. The emerging heterogeneous landscape slide admits the fact that the industry momentum in both hyperscale and hyperconverged storage variants has been and continues to be towards proprietary network block storage protocols. Such providers have shunned both legacy and emerging, like NVMe-oF fabrics, network block storage industry standards. Simple block storage does not suffice for them. Isn't the shown emerging landscape a declining niche? So there's somebody saying, great, thanks for NVMe, or as Douglas Adams might have said, thanks for all the fish, because that, it is game over. The hyperscalers are not adopting it. Is that a fair criticism?
I think that we have to consider that the hyperscalers did not deploy technologies like Fibre Channel and iSCSI for a lot of the reasons that Erik talked about, cost being the main one for Fibre Channel and the complexity of implementation for iSCSI. And instead, they developed their own, mainly because they needed the capability at a cost point they could afford to do at super hyperscale, right? Mm-hmm. Also, figuring into that is that they do a lot with DAS, right? So many of their applications, this is legacy. Hyperscalers, as they started out, still today, dramatically, a lot are DAS based. So it's just working off local drives. But like Fibre Channel tradition is moving towards Fibre Channel over NVMe, and not quickly, but slowly. The hyperscalers are looking at NVMe and NVMe-oF fabrics and seeing, wow, this technology is standardized. It works across everything. It's super high performance. And so, there's a lot of movement there that I really can't go into detail on because of NDAs, but I think that it's a similar kind of Fibre Channel moving to new storage technologies and hyperscalers having their legacy that is at super high scale that they also have to move and can't turn a switch and do it overnight.
Erik, you got 15 seconds.
I was just going to agree with what Rob just said primarily. But when I'm thinking about that question, I keep coming back to my customers and who my customers are and what their needs are. And so I appreciate the sentiment with the question, and I do like a good poke in the eye question. I'll just say that for my customers, this is gonna, I feel like we're optimizing something for their use cases, and so this is less of a concern.
Okay, Nishant?
Very quickly, I think, first of all, if you think you know everything that the hyperscalers do for storage fabrics, I wouldn't say that. There's a lot that is said and there's a lot that is not said. Number two, there are always base protocols like NVMe fabrics, and things are built on top of that for specialized applications. Number three, I can tell you, if you just look at the bunch of hyperscalers that were involved in the development of NVMe over TCP as a standard, just read through the list and now tell me why those hyperscalers would invest so much in building NVMe over TCP as a standard and not use it.
Okay.
Okay.
Thank you. That's an excellent response. But as you leave, ladies and gentlemen, if you could rate this webcast and provide us with your feedback, that would be really helpful. The webcast and a copy of the slides are going to be out in our educational library, and we're going to do a Q&A. So all the other questions we didn't get to, and there were a few, and that one, the poke in the eye one, will be answered on our blog at SNIA-at-a-Glance.org, and you can follow us on Twitter at SNIA-NSF. Thank you very much to Rob, to Erik, to Nishant today for their very interesting talk on NVMe. And I would like to thank you, the audience, for coming along today and asking such intelligent questions. In the meanwhile, thank you. Good morning, good afternoon, good wherever you are, and we'll speak again. Bye just now.
Thanks, Alex. Thanks everyone.
Thank you.